Hello, everyone. My name is Paul Bemis, and I am the president of Applied Math Modeling. In today's webinar session, we're going to be talking about interpreting CFD results, data center design applications. I am with my colleague, Kevin, who's going to be taking questions from you. So if you have questions at any point, please just go ahead and put them into the chat, and we'll go ahead and try to answer them as we move forward. So let's go ahead and begin. Just a little bit of background on our company. We are Applied Math, been around since 2008. We are a partner of the Ansys Corporation. We build value-added software on top of their base technologies. So all of the measures, the solvers, and post-processing is provided by them. We focus on delivering cost-effective simulation tools for data center design based on a SaaS model, software as a service model of delivery and support. We're all CFD experts and finite element experts. My background is with both those companies, Ansys and Fluent. And my background is also in high-performance computer design. So thermal performance in a data center, primary goal here is keep things separate, keep the hot and the cold. We're talking here about air-cooled data centers. Now, I'd like to also point out that even if there's liquid cooling, direct-to-chip liquid cooling in your data center, or even if there is in the future, you will still also have air cooling to deal with. So air cooling is not going to go away. It is just going to be complemented by liquid. So these issues that I speak about today will persist no matter what the data center does, because there's always components that are going to be air-cooled. Primarily because of cost, it's cheaper to air cool, and also because it just doesn't make sense to liquid cool every little component in the machine unless you immerse it. There is immersion cooling, but that's quite expensive and not widespread in its use. The reason you want to keep these airstreams separate is it makes the system more efficient. In particular, it makes your air handlers more efficient. Heat exchangers like a lot of difference in temperature, delta T. The higher you can get the delta T on the air handler, the more efficient it will be. It'll transfer heat faster and better. That will lower the cost to operate the entire data center. But it does require some attention to where the air is in the room, where it's going, and understanding some basic parameters that I'm going to just define for you here, just kind of remind you of, I think. So this is air management. This slide comes from the DCEP training, which I would recommend if you haven't taken, you probably should. DCEP stands for Data Center Energy Practitioner Training. It's put on by the Department of Energy. It's a web-based training that you can take. And they define these two issues of recirculation and bypass airflow. So here's an equipment rack right here. And if there's not enough air coming from a source, a cool source, like a floor tile or somewhere else, a fan wall, this rack will just recirculate on itself. These fans are going to run. It is going to pull air. It's going to pull air from wherever it needs to pull it. So it's just going to go right around in a circle. We call that recirculation airflow. Bypass airflow is the opposite. You've got too much air on the front side for some reason. And instead of the rack pulling it through directly, it goes over the top and over to the back. But both of these are bad. Recirculation is your hot is entering your cold, and so you're going to eventually run into problems with air intake temperature over here. Bypass, really what you're doing is you are effectively reducing the return air temperatures of your units, your cooling units. In this case, your rack units are bypassing the air and going into the cooling unit and reducing its temperature. If you reduce the temperature of the return, what happens, of course, is that the air handler is less efficient than it would be otherwise. Okay. So air management is quite important in a data center. You need to have adequate thermal conditions for rack inlet temp. That's what we look at. That's the ASHRAE spec is rack inlet, based on rack inlet temp. Also, from an energy management point of view, The better you handle your air management, the more efficient the data center will be, and it will reduce the energy consumption of the data center. I will talk about that in a moment, but the chillers become more efficient. The fan energy drops. Remember, the fans are cubic in their relationship to mass airflow. So as the fan energy goes up in order to supply more air, the power required to drive those fans goes up by a cube, third order relationship to mass airflow. Chillers, the efficiency of a chiller, if you return the hotter temperature, so you want a really hot temp coming back to the chiller to be dumped to the atmosphere. That's what chillers do. They pump heat into the atmosphere. And in general, you'll get about a degree for every degree C or centigrade that you increase the return air temp, you'll get about 1% performance improvement in the efficiency of that device. That's a very coarse rule of thumb and does not take into account economizers and other things. So it will be at least that. So the idea is efficiency. The last thing is we talk about capital management. Improving the energy efficiency of a data center makes your equipment last longer. It has to work less hard, or it doesn't have to work as hard, however you want to say that. So it lasts longer, simply. In other words, if you don't have to turn on the compressor because your return air temperatures are high enough that you can simply dump it to the atmosphere without having to compress it in a Rankine cycle, then your compressor is going to last longer. That's all. So it does affect your capital equipment to manage your air effectively. Okay, so there's a couple of metrics that we're going to be talking about. These are also taught in the DCEP training as well. One of them is return temperature index, RTI. These were developed early on and part of the DCEP training. My old friend Magnus Herlin worked on these as well as others, but they came out of some work with Lawrence Berkeley Labs and DOE. And you can look at them two ways. This one, I think, is probably the most important, RTI. You can look at it as a flow rate, or you can look at it as a delta T. The delta T is a little harder for people to understand. I'm a fluid dynamicist, so I look at it from an airflow point of view. They are symmetrical because they equate to the same. But here what we're looking at is rack flow rate divided by air handler flow rate. Okay, so the way that this works is that the rack flow rate always needs to be less than the air handler. You need to give it enough air. A perfect situation would be these were identical. And you see, if these were identical, it would be 100%. But it's important that they're less than 100% because you want this number to always be a little lower than this number. Let me go back for a moment. If you had a choice between this one and this one, you really want this one to be there. In other words, you want to supply a little more air than is really needed by this rack because you don't want it to get hot. If you're doing this, if you're below what the rack appetite is, you're going to have this situation. That's going to result in hot spots. You're going to have reliability problems. Furthermore, this rack will start to ramp up in speed. Its fan speed will come up once it senses high intake temp. So to have a high bypass airflow, you need to have this one greater than that one. In other words, RTI should always be less than 100. And if it's greater than 100, you've got recirculation, as I just described. If it's less than 100, you've got bypass. But this provides you a little bit of room for things like N+1 or other asymmetries that may happen in that system, okay? So now the next metric is RCI. RCI is rack cooling index. You don't really need to remember how we did it. It's not that important. What is important is that you try to keep it within the good range, the good to ideal range, 95 to 100%. We calculate this for you. This is something we do in CoolSim, so we give you this number. This is how many hotspots are there and how big is the magnitude of the hotspot. You want the range for, and I'm using Fahrenheit here, so apologize to my international customers, but I am in America. So, and we use Fahrenheit. So The recommended inlet temp for servers is 80.6 on the upper side and 89.6 for allowable. And most people do not run over here. Most are running over here. So you want your rack inlet temps to be 80 or less. The magic number is actually 77. That seems to be a rule of thumb as well. Around 77, the fans and the servers start to ramp up. So you want to keep it down around that 77 to 80 degree range. So what you're trying to do in these systems is you want the air supply temp to be as high as you can get it, because that is in fact what gives you the high returns on the air temp. Furthermore, the higher the supply air temp, the less work you have to do on part of the chiller or the cooling unit. The other piece is you want to keep the supply flow rate as low as you can. These two are the key to having an efficient data center. However, they work against one another, right? As you slow down the air, the temperatures start to rise on the inlets. As you increase the inlet temperatures, you need more air. So they tend to work against one another in a sense. You have to monitor them both. And the results are you have better chiller efficiency, reduced fan operation, your servers are happy, your economizer utilization increases, because remember, the economizer in the cooling loop is going to dump heat to the atmosphere when it can, and it can do it as long as the return liquid temperature is greater than the atmosphere by enough of a margin so that it can dump it effectively. So economizers will help you a great deal. Same with dry coolers. Dry coolers are essentially an economizer. They go into economizer mode where the chiller's not compressing and you're just passing liquid through the heat exchangers. Now, I'm also going to just remind you of Bernoulli, our old friend, our old Italian friend, Mr. Bernoulli, which is represented in this equation. So velocity squared, you don't need to worry too much about this one. This one has to do with height. And here we have, of course, pressure. So we have two pressure variables. This is a static pressure over here, and this is dynamic pressure over here. And it is those two in a data center, because we have no height in a data center. It is those two that combine to give you total pressure. And it is fairly constant. In fact, we model air as an incompressible fluid in the system. So total pressure is the sum of static plus dynamic, and you see those two variables right there. So I'm pointing that out to you because I'm going to bring it up as we go through the results. I'm going to talk to you about the trade-off between dynamic and static. Makes a big difference in the data center design. Unfortunately, the air comes out of these big pieces of equipment called air handlers and floor tiles and things, and as a result, it comes with velocity. And that velocity is not your friend. It tends to reduce static pressure. So when you create a model for CFD, I'm just going to remind you that avoid the small details. They're not going to be that important. And what I mean by small details is that oftentimes I have users who want to treat the system as a CAD system and include every little thing in case, every little piece of geometry in case it makes a difference. But what is true is the dominant parameters take over. It is the dominant parameters that matter, like placement of inlets, the velocity of the inlet, where the cooling units are, where the racks are. Even the size of the rack doesn't matter all that much, to be frank. You don't have to get the rack to be exactly the millimeter that comes from the manufacturer in, because it is the heat load in the rack that's the dominant parameter, not the geometry of the rack. Within reason, within reason. I mean, half a size of a rack, a rack that's only, say, 4 feet tall is different than one that's 8. But one that's 1,180 millimeters is not any different than one that is 1,000 millimeters. It's just not going to make a difference. The height of the room is important. The plenum size is very important. The ceiling return is very important. Its depth, placement, and size of rack in general, the magnitude of it. Is it a 42U rack, 46U rack? That's important, but not the millimeter. You don't have to take it to the millimeter. Generally, you want to begin with average watts per rack because that allows you to get a feel for the overall parameters in a data center. So don't be worried about getting the wattage within a rack to a 1U level of granularity. It's not going to matter all that much, at least in the first pass. It may be that later on you want to dial it in a little tighter and be able to predict your heat loads in the rack with more granularity. But in the first pass, it's not really that significant because you're just trying to get a feel for what's going on in the room in general and make sure you have enough air. And if there's hot spots in the room, where are they? You can see all of that without dialing into the detail on the rack. Can always do it later. And you use the model to determine what the optimal operating point is. In other words, how low can you go on airflow before you start to run into trouble? How high can you go on supply air temperature before you start to run into trouble? So the CFD model is a tool to allow you to understand the basic layout of the data center, what's going on in the data center, and what the big parameters are and why. The details, exact details of what is in the rack, again, can be added later. The governing equation for all of this is that heat transfer, Q, is the mass flow rate of the device times the density times the specific heat times delta T. Now, these two tend to be fairly constant. They don't change much. Density doesn't change much. We're not compressing it much. Density will change with altitude, but it's constant for the data center. You know, it doesn't change as a function of time. It's constant. Specific heat is constant. So it's really these two, the flow rate and the delta T, that determine the heat transfer, Q. Now, that's true for the air handler. It's also true for the server itself. So this is the governing convective heat transfer equation that data centers use and rely on. It's one that if you're not familiar with it or don't quite remember it, it's one to keep in mind, okay? I also simply wanted to take you through a rack just to point out that racks leak. Racks are not perfect. They have problems like all of us do. You have a rack rail that sits. So I'm transparently looking through a model of a rack. And you see the rear door and the front door. Doors don't matter that much. The percent area open on the doors ought to be high enough so that they're not restricting any flow. If they are, that's a different problem. You've got servers in here. I have the servers identified, at least in this particular model. I did identify the servers. Then I have something here called a rack rail. And that rack rail is important because it tends to leak. The servers are generally 19 inches wide, and I know that's a funny number, but it's history. A lot of this stuff was done in the US by IBM, and so they made their servers 19 inches wide. They've been 19 inches wide forever. Sometimes they're a little wider, but generally you get them at 19 inches. And that means you have this rack rail that sits around. It's generally about 3 inches on each side. It's generally 4 to 6 on the top, and it's a little, 3 to 6 on the bottom. And this goes to the floor, by the way. A lot of people don't look down on their racks, but down low is important because that's where the cold air hangs out. It's down low because it's a little denser. Okay. So these things leak. Rack leakage can be an issue. It certainly is for contained systems. You have to model it. You should model it. And you need to add that in for best practices, okay? All right, so enough of all of that stuff. I'm going to now take you through, in the time we have remaining, 2 different data centers, and we're just going to look at results. I mean, the point of this webinar today is to take you through results and make sure you understand how to interpret them. It becomes a second nature somewhat to me because I've been doing it long enough for data centers, but I realize that not everybody does this every day, so I'm going to show you 2 different systems. The first one is this older data center. This is an IBM data center, an old IBM data center. I'm going to take this URL and I'm going to put it in the chat so that you can follow along if you want to. One of the great things about CoolSim is that we can share results. So I'm going to share these results with you via hyperlink. So if you go to the chat in our web meeting today, in our webinar, you're going to be able to follow along with me if you like. You can also store it and put it in a bookmark or something and keep it for later and show it to people, impress your friends with it. It will persist, so it'll be there in the future if you want to reference it. So this is a data center. I'll show it to you in a moment, but this is a set of output only for a particular data center. This is a raised floor data center. It's not contained. And I've done 4 runs here. Now, in CoolSim, you can set up 4 variations at once that will all run concurrently, and you can therefore take a look at different settings, different parameters. We give you a summary page here, and so here's the summary page of these 4 runs. And you can see in the first run, run 0, I left everything on. So all the units are running, all the cooling units are running. They're all running at their relative capacity, maximum capacity. Remember, in CFD modeling, we want to know the worst case conditions. We want to know what the extremes are. So these are all running at full speed. You see the supplier temps are probably, in this case, measured. I've got one at 56. So the way to do that is to go out and measure. If it's an existing data center, you can take some measurements on supplier temp and just set the supplier temp. The equipment itself will have its own CFM. So you'll be able to look up the CFM, the max CFM of the equipment. So if you know the CFM of the equipment, which the cooling unit generally will tell you what its CFM is, either on the front panel or through a specification. If you know the CFM and you know the supplier temp, you've pretty much dialed that guy in. He's in. Same for the others. Right? So I ran the first one with them all on. Then in run 1, I shut off a unit. Now this is one of the heavier units. You notice this one's at 17,000. That means it's dumping the most heat of anything in the room, at least one of them. So that one, shutting that one off is going to probably, this is an N+1 test I'm doing right here. Will it survive if I shut one of these things off? Because they have to shut off for maintenance. They have to, sometimes they fail. You have to understand that they will at some point need to go down and be replaced. And you need to understand if your worst case loads will hold up in that situation. And then over here, I shut off a different one. I shut off one at 15,000, then over here, one at 14,000. Now, to be completely thorough, you would have to go around the room and shut off, I would need, whatever, 1, 2, 3, 4, 5, 6, 7, 8 variations. And that would be 2 runs of CoolSim. That's still not too bad. But you can almost always guess where the problem is going to be, particularly if you look at the first one. So let's take a look at run 0 and just have a look. So this is what run 0 looks like. You just click on run 0. CoolSim reports always look like this. They consist of 2 parts. Over here is the alphanumerics area. This is where the data is, the alphanumeric data. And over here are the 3D files. So let's first take a look at our energy report. I'm going to go right here because I'm going to use these metrics that we spoke about. So you see RTI here, 73.242. Now that tells us, and we put a little mark in here, that tells us we have bypass airflow. That tells us that we have more air than we really need by quite a bit, 20% more, 25, 30% more air. We're in an orange region here. It means the bypass airflow is high enough so that those returns are getting cooled off. That's what that's telling us. Even though, look, our RCI high is 98. I've got a couple of hotspots here. That's a little unusual. I mean, why, if I'm supplying so much air here, do I have a few hotspots here? And also, I'm running way too cold. You see that this would always be 100% unless it falls below the ASHRAE standard. And in that case, we're gonna come down. So this is not a great look. Now up here, if we look at the detail on that, we'll see that we are supplying 115,000. I'm sorry, it's CFM, my friends from Europe. 115, but I only need 84. So I'm oversupplying, as you can see, by quite a bit. And that was evident. I'm showing you the numerical result of this number. Now, the next place I generally go is, okay, I can tell, I know what I'm going to see. I'm going to see in the 3D view that in some places I'm too hot, in some places I'm too cold. So let's go take a look at our data center. First, I'll show it to you as a shaded data center. So this is our data center. This is what it looks like. It is perimeter crack units. In a data center, it is a raised floor design. These are the cooling units. You can see the red is the return and the blue is the supply. These are the racks. It is a raised floor design, and these are perforated tiles along the Now, it's an older data center, and so things aren't lined up perfectly. You see, I have some racks that are not lined up with the others. That's not a great thing, but that's typical of an older data center. We have some underfloor cable trays that are going to cause some issues with flow. We have a fairly narrow subfloor. If you look, that subfloor is not very deep. Again, we go to Bernoulli, right? If the subfloor is not deep, you're going to have a high velocity, right? Because the cross-sectional area is narrow, and that means in order to get the mass flow through it, the velocity is going to go up. When the velocity goes up, the static pressure drops. Remember, they trade off with each other. Total pressure is static plus dynamic. So as this air comes rushing out, it's going to have high velocity. That's going to cause some issues. So there's my room itself. Now, over here on the left, we have all of these images that are naturally generated by CoolSim. I didn't do anything special here. All I did is hit the run button. These all come back to you as part of output. And I'm going to take a look at the ASHRAE recommended range for this particular data center. Now here, this is what we call kind of a go, no-go gauge. If any of you remember that, in mechanical engineering, if you had a gauge that said that something conformed or didn't conform, that's what that refers to. Here, this is a conformance plot. Above 80.6, we're out of range. Below 64.4, we're out of range. You can see them both in and out. Now, that is because it is a naturally convective design. I'm not containing anything. Over here, I'm too cold. These units are supplying air that's below the range. That won't hurt the IT equipment, but it hurts your energy efficiency terribly because it makes it work much harder. We're also seeing a little bit of red spot here. This is a problem. This means that my racks are getting a little bit warm around those edges. Now, in reality, it's probably okay because it's unlikely. I've got a server up there anyway. Even if I did, it's borderline. It's right on the edge of compliance. So this one's probably okay in steady state. Over here, I'm having a little trouble on this edge. This is because I believe this unit is too close. We'll investigate that further. But I can see from this base model that it's not perfect. And this is quite typical of a non-raised floor design. So that's what's going on. Now let's go take a look at some of the airflow and you'll see why. Down here at the bottom are pathline plots. These are very handy in my estimation for understanding what's going on. Let's first take a look at air from tiles. We separate them to make it easier to see. But here's airflow coming from tiles. Now, you expect the air would come up out of the tile and go into the server. So the way it's supposed to look is over here. And I can hide some of these things so you can see a little better. But you're supposed to have the air come up out of the floor. By the way, that was a right mouse click in case you're following along. You can come up out of the floor and go into the server, and they should stop right there. That's it. It should just come up out of the floor and into the server. But you see, it's going a lot of other places here, and it's because we have bypass airflow. It's bypassing the rack. So there you can see bypass airflow in detail. It's going up out of the rack, and it's going back into the return of the air handler, which is lowering that temperature. And this is a temperature chart, and you can see here that it's coming out and it's being mixed in. The hot is coming out of the backside. I'm not showing the hot right now, I'm just showing the cold. And it's causing the returns to be cooled off. So that's not a good thing. If we're supplying it at 55, remember that this device right here is going to give you at least a 25-degree increase. So that's going to give you a return of about 80, should. And here I'm not at 80, I'm below 80. It's cooled it off, okay? And that's bad for your air handler. So then let's take a look at path lines from the hot side. And here I've got a similar problem. I've got the hot air getting here. The hot air is coming from the rack. You want it to be nice and hot going into the return, but that cool air is coming over the top and cooling it off. So although it's coming out of the rack fairly warm, upwards of 90 degrees in some cases, by the time it gets back to the cooling unit, it has cooled off. So that's a problem when you have a mixed environment like this. It doesn't allow you to separate, and therefore your delta T's are poor. And you can see it if we go back now to CRAC performance report, which is the numerical side over here on the right. You can see those average return temperatures not really being where you want them to be. Remember, if your supply temp is 65, your delta T should be, let's assume it's 30. That's a good server, dumping 30 degrees. This should be 95. Any one of them, right? If I'm 65 here, you add 30 to that, this should be 95, and it's not. These return air temps are low. I've got a delta T here of 13, 20, 20, 26. Not even 16, right? Yeah, 14. So the delta T is poor on the system. And we're also getting an alert here, 96 on this unit. CRAC 45 is operating near its capacity. So in CoolSim, this will start to turn red if the capacity exceeds the nominal rate of the cooling unit. And here I'm on the edge, 96. This is probably a 95 kilowatt device, and I'm near the edge. In other words, even though I have more cooling capacity than I need, and also, sufficient temperature, I'm still having asymmetry. You see the asymmetry in those cooling units over here. In other words, this unit right here, CRAC 45, is delivering 49% more than the average, where others are performing minus 50% of the average. So this variation over here shouldn't be that great because it means there's a dependency on a particular cooling unit. CRAC unit 45 looks like the worst one to me. In other words, if I were to lose a cooling unit in this system running steady state, just as it is, which one would I be worried about? CRAC 45. Why? Because it's already working near capacity. It's working harder than anybody else in the list. And so if I lose CRAC 45, it's going to be problematic. So that's part of the issue here. And I didn't fail CRAC 45, did I? CRAC 9, I should have taken down 45 and an N+1. But let's keep going. I took down one of the big ones. This is one of the big ones. This is a 17K flow rate. So let's go take a look at run 1. So now in run 1, just to remind you, I'm going to show you the path lines from the cooling units here. So you see, not all the cooling units are delivering. This one's off. And this one over here is the one on the far end, and it's one of the big ones. So this is a 17,000 CFM unit, and I've switched it off in this run, so it's not delivering air. So this path lines from cooling units tells you which ones are on or off by just looking at it. The other thing I wanted to show you is this underfloor pattern of a swirl here. This is not unusual. Now that this one's off, there's an asymmetry in pressure. So this comes in swirling like this and then comes around and creates a vortex underneath the floor. The vortex is going to cause a low pressure in the center. So these tiles are not going to perform well because of that low pressure. So that's what the air coming in looks like. Let's go take a look at the recommended temperature. This is always one I look at. And you see I've got problems. I've got problems over here because the air is not coming out of this unit, and so these are failing. These are failing pretty badly. If I go back and take a look at my energy report, you see that I still have bypass airflow. In general, I'm still supplying more than I need of air. But I've got a big problems with hotspots, right? I'm way down on my RCI high, down around 55, 60%, and I just showed it to you. I'm no longer too cold, but I'm too hot, and I have enough air. So this is a case where you would normally do your hand calculations and say, I'm fine, I have enough air. In fact, if I look, I'm delivering 15% more air than I need to the room, so my hand calculation says I should be fine. If you're looking at just, cooling capacity versus load in the room, your algebra would tell you that you're in good shape. But because the distribution in this room is so poor, you have hotspots. You can see them in the 3D. I showed you this one already. Let me also show you the performance on tiles. We give you flow rate on tiles. This is another important plot for raised floor design. Not all floor tiles are equal. And what you see here is, and what I'm going to do is use the Y key if you're following along. So Y gives you a top view. N, as in Nancy, gives you perspective, turns off perspective. And you can see here now that the flow rate coming out of those perforated tiles varies quite a bit across the room in this case. Very asymmetrical, higher in the middle. Why? Because the velocity is lower, and so the static pressure is higher there. And here you see this is where the swirl is under the floor, and you see these tiles performing really poorly. They're down around 200. I mean, I've got a factor of almost 4 between one tile and another in this room. So these are running around 2. These are all same percent area open, by the way. These are running at 200. These are running at almost 900. And that's because of Mr. Bernoulli, right? That the amount of air coming through there is proportional to the static pressure. And in some cases, you have high dynamic, or you have a swirl going on with low pressure in the center of it. So these tiles are not performing well. The result is you have this problem where air is not coming out of those tiles. So if we look at path lines from tiles down here, these path line plots are really helpful. Look at path lines from tiles, you will see that I'm not getting air out of some of these. And if you're following along with me, you see I still have bypass airflow, even though, you know, I could really use some over here. It's all over here. It's in the wrong section of the room. And yes, you could go into the room and damper these down and try to manually adjust it. But it would be challenging. It would help. But look what's going on over here. And by the way, if you're following along, you can right mouse click and just hide body. You can do it a couple of times and it will successively. But there's your problem right there is air is not really coming out of those tiles very well at all, causing problems in this end of the data center. Okay, so that's run number 2. And let's go back and see what we did in run number 2. We turned off one of the 15,000 units. So these are pretty much all going to report similarly. And my advice to you is to first look at this one. First look at the energy report and understand what's going on. You can very quickly understand your data center performance by looking at this set of parameters, why it was developed. So here we have RTI of 84. That means I certainly have enough air, but I've still got hot spot problems. So I've got some issues. Now, this generally speaking is not too bad. You're above 90. You're not too cold, but you've got some hot spots. So let's find out where they are. This is always the one I go to is ASHRAE recommended. And then I take a look at where they are. And I'm already beginning to understand that this end of the data center is problematic. It's problematic for a couple of reasons. One, this distance is so close that when this thing is running, the underfloor velocity here is really high, and that's causing problems. So again, even though, and you'll get to know your data center. Once you build a model like this, you get to know what's going on. And again, I'm average watts per rack here. I haven't gotten into rack detail. I don't need to. As long as I know the average watts per rack and what my air handlers are doing, I can run models to gain insight about what's happening in the data center without getting too carried away in terms of time or detail or level of complexity. So we've got problems over here. Let's go see what the path lines look like coming out of the floor again. So this is path lines from tiles, and I want to show you in this section of the room, it's a clear illustration of the Bernoulli issue. So again, I'm going to right mouse click, hide body, right mouse click again to hide body, and you see what's going on. You can see the momentum. So the air is coming out under the floor and it's trying to come out of that tile. But you see it wants to continue in the direction that it's headed, right? Because a body in motion wants to stay in motion unless acted upon, right? So what's happening is the air is coming along the floor. The tile is open, but the air, the velocity is very high under here, and it bends, and it just doesn't get to this upper section of that rack. And that's why that rack is having problems, is because by the time the air slows down, it's gone by it. It just blows right by it. And for those of you with experience in a data center, you'll often find that if a tile is over here near an air handler, you can take a piece of paper and put it near the tile, pull it right down to the tile. In other words, it's pulling air out of the room instead of putting air in the room. That is not an uncommon thing if you have a narrow floor like this one, and you have perf tiles too close to air handlers. It's not a perfect world. Unfortunately, the air handler has a certain size, a physical size that the air comes out. That physical size determines its velocity, its exit velocity. Bigger units have bigger outlets. But at the end of the day, it's a velocity issue that you're dealing with. You have to get the air into the room, and that messes up your pressure balance. So that's primarily what I wanted to show you on this one. We can look at path lines from the cooling unit, from the racks, and you'll see these are starting to recirculate on themselves up here. So you see what's happening is now I'm having recirculation, airflow. It's going up over the rack and back into the inlet. You can see these inlets are pulling air in. So if this is a temperature range, so we're at the 80-degree range, and it's pulling it right in over the top. And that's what causes this picture to occur. All right. All right, so you have that set. I wanted to go through those with you. I don't think there's anything else here of tremendous significance. So let me go to the next set. Again, you can do up to 4 of these. If I had done it again, I would have shut off the big one. Look at your steady state runs to see where your issues are. I would have shut off crack 46, but you can always run it again. So let me close that. I'm going to go next to a high density because these issues are the same regardless of the design. So here I'll take this one again and I'll put it into the chat so that you have a copy of this one as well. Again, these persist. You can keep these, you can bookmark them, you can share them with your friends and neighbors. But let's take a look at this data center. First of all, let's go see what it looks like. So up here under 3D models, we have something called shaded. Shaded allows you to see what this data center looks like. This is just a shaded representation of the geometry. So this is a fan wall design. This is one of the more high density kind of designs I'm seeing a lot of lately. And here you have fan walls. Now, basically what's happened is as the rack appetite for air goes up, remember that it's generally wants about 125 cubic feet per minute per kW. Rule of thumb, right? Use 100 if you want to do easy math in your head, 100 CFM per kW. That assumes a delta T on the rack of about 30, 35 degrees. Now, what happens is if you have a rack like these that are running at very, very high loads, I'm seeing racks now in the range of 40 kW, and I'm being told it's going to go to a megawatt. But 44, 45 is about the maximum you're going to be able to dump efficiently in a data center for air cooling. And so you really can't use a raised floor data center in this because there is just so much air that your plenum would have to be extremely deep in order to keep that velocity from being too high. And that's expensive. So the alternative is fan wall units where take these devices. These are very large fans with a coil in them. They're really just fan coils. They're blowing air into the room. And this is a hot aisle contained. You can see the containment here. Hot aisle contained. These racks are blowing air into the hot air, into the hot side and up and through the ceiling. Return plenum goes up around like this. So this is how these operate. Air from both sides, fan walls. Now, again, that looks like a pretty good design in steady state. The question becomes what happens in N+1 or N+2. In other words, these are very heavy units in terms of mass flow rate, and we need to be concerned if we lose one of them, what does it do to the airflow in the room? How does the symmetry of airflow, how do my rack inlet temperatures look when I lose one of these units? So let's go find out. First of all, again, let's look at my summary. And my summary, I've got everything running. Everything's running at full speed. And I'm supplying at 77 degrees Fahrenheit. Now that's pretty high. Remember, my upper number is 80.6. So that's pretty good. I'd love to be able to supply at 77 if I possibly could, because that'll make my cooling systems much more efficient. Let's go take a look at run 0 and see what we find. First one, again, I look at is energy report. And I see that I'm running pretty good here, 95. So that's very close to matching, very close to 100. In other words, my demand air by the racks is just slightly lower than my supply. I'm oversupplying by just a little, which is a good thing. And you can see my RCI high is great. My RCI low is great. This thing's perfect. It's perfectly matched. Now let's go take a look at our rack inlets. They're always the thing I look at right away. And I see that everything's green. The world is green. We also do a full range up here too. This is not a compliance plot. This is full range. Here we take the values that we see in the result field and spread them out across color. So that means the result field saw a low of 77 and a high of 81.8, 82 degrees. So that's just close, very, very close to borderline, but you see it's just really a couple spots on the edge. So it did pass the compliance test. But you can see what's going on here a little bit, and you ask yourself, well, why is it warmer on those edges? What's going on that's causing that? And this begins to tell you again about the same topics, leakage and velocity. So let me just show you path lines of supply air. I always go for path lines pretty quickly because they tell you a lot about what's going on. So here's my supply. And this is a velocity plot, feet per minute. Again, right mouse click to clean up some of this so you can see a little better. So here's my air coming rushing in from those air handlers. And you see they're pretty high velocity. I mean, this is in feet per minute. So again, sorry about the English numbers, American numbers really. But you can see here that the air is coming rushing in at fairly high velocity. And so what happens is, as that velocity comes rushing by around these corners, it's going to create lower pressure in this region. There's a lot of air, a lot of fast air coming in, causes lower pressure right in this region right here. And this is your rack rail. In this model, what I've done is I've modeled each rack really as 19 inches wide, because 19 inches is the width of the server. Then you have the rack rails leaking, and then you have the containment leaking. They both leak. The amount of leakage is proportional to how well it was installed, but you have to assume some kind of leakage because they do. I think I have this one probably set at about 10% because that's not an unusual number. 10% leakage. It's hard to know without laboratory testing. But I did let this membrane leak right here. And that you can see that lower membrane right in that rack area. I put a membrane in there and I'm letting it leak right there. And the reason for that is it's realistic. That's really what does happen. And it also shows you the effect of this airflow. So let me just take you to a plot here. I'm going to slice. These are slices of temperature. I'm going to slice this one at, let's take it pretty close to the bottom. This is 3 feet from the bottom, and let's see what's going on here. And again, I'm going to use the Y key. I'm going to use N as in Nancy. And you see here that I'm watching as the air comes by, I can see leakage. I can see this rack rail beginning to leak because high velocity air is coming by. High velocity air is low pressure air. Remember, velocity and static pressure trade off against one another. The lower pressure here caused by the high velocity is pulling. There's actually a pressure delta pulling the air through the membrane. Okay, and it varies depending where you are. Up here, it doesn't look good. I mean, that one looks like it's leaking. That's why you're getting those conditions. Now that's steady state. I mean, everything's working perfectly here. Now what happens when you shut off a cooling unit? When you shut off a cooling unit, this thing becomes asymmetrical, right? And different effects start to happen. So let me show you that. So again, in the base case, we have everything on. In this case, run number 1, I shut off one of the fan units at the end because my supposition is an end unit is going to be more problematic. So let's go take a look at that end unit. Here we're looking at run number 1. Okay. Now again, let's go look at our energy report. Uh-oh, we're a little bit out. We're at 101.99. Not bad. I mean, it's kind of perfect, to be honest. You want it to be 100. A little bit of recirc, yeah, it depends on your supply temp. You can see here my RCI high is pretty good, 99. So that's not bad. So this held up pretty well to an N+1 test, despite the fact that it's close. But let's go look at the details. Let's first of all see where it's falling out of compliance. And you can see right back where I was earlier, edges. Why? Because that pressure differential is highest near the air handler because I have high velocity air rushing by there. And depending on the symmetry of where that unit is off, that will change. So let's see where it's off. I always go down to my from cracks plot because I want to see the airflow coming out of those cooling units. So I shut this one off. You know, I don't know until I look. Whenever we do consulting reports, I always show this picture because it's important to know which one's off so you can see what's going on. The great thing about CFD is it allows you to visualize something that is invisible, air. And what's going on here is because this one is off, air coming out of this one is rushing further across the room at higher velocity than it was before because there's no pressure over here caused by that fan to slow it down. So it's going ripping by this set of racks, causing a pressure differential there. And this pressure in here, remember you've got two high-speed airflows coming at each other, and they meet in the middle and go to zero and up and out, or near zero. So it's not unusual that your pressure in your hot aisle is a little higher in certain areas than the pressure in the cold aisle, even though you're supplying more air than you need. It becomes localized. And that's the power of CFD, is understanding that local behavior. Mathematically, you can say I have enough cooling capacity and the numbers should add up algebraically, but because fluid dynamics is a non-linear science, you do have these effects that will occur that are not obvious if you just do the math, just do the hand calcs. So again, let's go back and take a look at a slice. We're going to do the slice at the same point. Here's temperature Y at 3.2. And let's go look at that same area. Again, I'm going to use the Y key, and I'm going to use N. And you see that guy leaking really badly over there. Okay, look at it. It's pulling the air out through this leakage membrane because the pressure out here is lower than the pressure in here. The pressure in here is caused by the racks. They're going to continue to blow. They're going to blow at each other and cause high pressure in the center. That's going to force a delta P pressure, and it's going to start to leak out. And as long as that leakage doesn't get too high, you're okay. The other strategy, by the way, is when you have an air handler down, drop the supply air temp. That's another thing you can do to help compensate. This one's running at 77 at the moment. Now, we also supply pressure plots. And so here's a pressure plot here at the same region. I'm not sure we're going to, pressure doesn't always show well without adjusting the scale. So let's do that again. And you can see, even though the scale is not perfect, you can see that the pressure in this aisle is higher than the pressure outside, particularly in that region right there. I mean, as you go towards red, it's higher. So you've got a pressure imbalance across this section of the room caused by high velocity air coming by. That's why it's important to, in fact, and pressure in general is higher in the hot aisle in that model right there than it is in the cold aisle. Not a situation you really want. So that's a kind of a view of that one. Let's take a look at our path lines from the racks themselves and see how that looks. And you can see these get a little crowded, but you can see some path lines. And let me again hide some of the things here so you can see that's a right mouse click if you're following along. You can see path lines beginning to come around. They're coming in through the leakage membranes and getting into the hot aisle. You can see some right here, for example. If we go down to the other end where it's problematic, you can probably see more of it. Again, I hide body to, whoops, I I hid the wrong one. I turned the path lines off. So there is a switch here for path lines. But that's in the upper left-hand corner if you want it. These are Ansys. This is an Ansys viewer. But you can see those path lines starting to creep out from behind and come around and wrap to the inside. There's one right there, coming around and getting those inlets hot. So I hope this has been helpful for you. It's 9:55. I don't want to, but let's go for this one. I shut two of them off in this case. This is an N+2 case, but I dropped the supply temp to 70. And I did this kind of intentionally to show you that you can cheat with supply temp in a worst case situation. So here, run 3, I've got 2 of them off, and you see my RTI is not good, right? My RTI is above 100, which means I'm not supplying enough air to this system. If you look, I'm supplying 490. The racks want 525. I'm off by quite a bit. But let's go look at my rack inlet temps. Do I comply? And the answer is yes. Why? Because I dropped supply air temp. So you can cheat a little bit. And when you get into an N+1 or an N+2 case, many of you who are managing data centers know this. If you lose an air handler, drop the supply air temp of everything else and just assume, that cold air is going to find its way to where it needs to be. And in this case, it did. I wanted to show you that it's not an unusual thing to do. I think there's still quite a bit of leakage in this room. It's just that the cold air being supplied is sufficient to overcome it. So if we take a look at path lines, we're probably going to see more leakage over in this area than we saw before. Let's see where the air handle is off. Oh, they're off over here. You can tell because there's no blue. Yeah, look at, you've got air leaking around and coming into the intakes here. We can see the same plot if we look at, again, y equals 6 feet. Let's put it at 6 feet. We can probably see leakage. So I've just turned this around and there's my, and you can see they're bleeding pretty badly. You see the air is coming through that leakage parameter, that leakage baffle and leaking into the room. You can see some temperature variations here. We're at 6 feet of height. This is a horizontal cut plane at 6 feet. Over here, we're problematic. This is where the air handlers are off. Over here, I believe, no, they're off on this end. But you see the PDUs are contributing to some problems here. The PDUs are dumping into the room. They're not ducted to the ceiling. So the power distribution units are dumping heat into the room as well. You can see it there. So I wanted to just go through this with you today. That's about it. It's been an hour. If there are questions, I would take questions from anybody in the audience. If you want to type them in to the Q&A or ask anything, that is fine. But you today have these outputs that you can look at on your own. You can always send us questions if you would like. What it does for you is allow you to understand the extreme cases and the flow management in the room. And making trade-offs between mass airflow and temp can help in failure mode conditions. So I don't see any Q&A. Let's see on the chat line. So I think, Kevin, that we don't have any questions here and might be enough for today.
We did have a question coming from Brendan, just asking if we have any more questions, what a good email would be to reach out would be. I think a good one would just be info@coolsimsoftware.com.
Yeah,
I can put that in the chat.
So I'm also putting it up here. I should have had that, but you can use info@coolsimsoftware.com and we'll answer it. We monitor that pretty closely. We'll answer questions you have. If you want a demonstration of the software or anything like that, please let us know. There's a question here about how local climate affects results. The local climate will affect results in terms of cooling capacity, because if the local climate if it's hot, your cooling units aren't going to reject to that environment very effectively, and you're going to have trouble with supply air temp. So it can have quite an effect. And I'm assuming you're talking about local outdoor climate. So I'll give you an example. I was working on a data center not too long ago where the customer thought that the walls were leaking because they had added up mathematically the cooling capacity they had, and they certainly had enough cooling capacity, yet on hot days, they weren't able to cool their data center. And when I went to the roof to see where their heat exchangers were, they were sitting on a hot black roof in the sun. And so I measured the surface temperature of the roof at 165 degrees Fahrenheit. And what happens, therefore, is the intakes to those cooling units goes up. And with high intake on the cooling unit, you have cooling capacity problems, okay? So the cooling capacity of those units, a chiller, heat exchanger, whatever you want, will decline as the inlet temperature rises. And it declines non-linearly, but it at least declines a percent per degree F. So your cooling capacity will decline proportionate to the ambient outdoor air temp. And that's true of dry coolers. Wet coolers, like evaporative units, are more sensitive to both. Well, they're sensitive to dry bulb and wet bulb. The wet bulb temperature affects them dramatically. So a short answer to your question, Bill, is it can affect you dramatically, depending on the situation. And this is why we're seeing a lot of external flow requirements and models being asked to run external flow, because the work that I just showed you has been done over the past 20 years, and we're getting fairly good at dumping heat out of the room. So we're pretty good at being able to get it out of the room. Now it's either on the roof or it's beside the building. And under a prevailing wind condition, particularly when a generator is running next to it, you've got problems. And that's, I think, going to be kind of the next area of interest for folks. So.
We just had a couple of questions as well from Shahid asking about grid independent study through CoolSim, as well as asking about solar radiation.
Solar radiation can have some effect because it rises surface temperature. And so, but there, in fact, I have a call now with a customer who's developed a product that will drop the roof temperature down a little bit so that solar radiation isn't as big a deal. Solar radiation can be a big deal because it affects the surface temperature of the roof. That's the primary issue. With respect to grid independence, data centers have the ability to be, this gets a little sensitive, they have the opportunity to be complementary members of the grid. But that arrangement has to be struck. That arrangement has to be made. In other words, the energy consumption of a data center can go up or down with load. In fact, it goes up or down by quite a bit with load. It used to be pretty flat, but a computer today, between load and non-load state, its power consumption can vary by a factor of 5. So you can shift load away from a data center to a different geography. You also have battery storage on site, quite a bit of it. So the battery storage can be helpful as well to ensuring that you're able to pull power from the grid only when necessary and rely on local storage otherwise. So there's quite a bit of discussion in this area about how do we integrate data centers into the grid. It's a little bit beyond what I was talking about today. I'm willing to have that conversation if you would like. But yeah, that one is a longer topic, so to speak. And yes, we will share this with you. We'll put this. We recorded this. We'll put it up on YouTube. We'll give you a link to the video. Okay. All right. Anything else, Kevin?
Ramesh had a question about whether if there's an ideal raised floor height, considering that there are some utilities below the floor. Let's say the vertical height of utilities does not exceed 6 inches.
Okay, so the question is there an ideal height? No. I mean, the bigger the better. How big what's your budget for raised floor, right? So bigger the better. Typically, I find them today at least 24, 36 inches is not uncommon. With respect to stuff in the floor, the first question I have is, why is there stuff in the floor? We should be doing overhead cables at this point, not underfloor cables. But if you have underfloor cables or obstructions, generally the rule of thumb is as long as the height of it is not greater than 30% of the cross-sectional area of the underfloor, then you're fine. 30% of the cross-sectional area. So take the height. I'll use round numbers, 10. So if the height is 10 something, I don't care what the unit is, and the obstruction is 3, you're good. If the obstruction is 4, then that's problematic. It's going to cause some velocity issues in the cross-sectional flow. All right, so there you have it. All right, I hope you found it useful today, and yeah, we'll do more of these like this. If you have topics that you'd like me to review with you, please let us know. Send us a note at info@. We'll do more topics like this. And I'm glad you found it useful. Thank you.